Where's your Excel thing again? Do you want to just email your Excel plot to me? Sure. Oh, sure, plus is it?
Does this mean that we just got something drastically wrong?
I mean, that's why I want to look at it, because I haven't seen any ones ever in all my years that have been negative. So, because that makes, like, no sense. But. All right. Yeah, we'll have to look at it after class.
We can always do it at lab too.
Yeah.
No,
I calculated the slope correctly, right? The unit of slope, this is unit of our mass, mole per second. And when I do the math, so this is the slope second, this is the our max, mole per second. So I can.
Oh, okay. Yeah, that's probably okay. I would have to do it myself.
Okay.
as you come in this morning, let's warm up with this problem and see how we do. How's this problem going so far? All right, well, that could be an issue. So I'll give you a few more minutes to work on. This is all one big problem. Yeah, so start with A, and then we can go from there. So how's this problem coming along? Does anyone want to throw it on the board? Although now that I said that, I don't have any markers, do I? Someone want to put it on the board of A. So how do we show that our observed rate law is consistent with our mechanism? All right, go for it. And then you can either put it on the far board. That might be better.
Okay, so what I first did for figuring out what the rate was, or the rate law, is looking at those steps and seeing which one's the slow one, because that's the one that's going to determine the rate law. So what we have is we have one bromine and one diatomic hydrogen. So it's just a first order, one bromine and first order diatomic hydrogen, and that's just the gas law, or the rate law for that part of it. And then, but we have a bromine by itself here, not a diatomic bromine, which is one of our products and reactants, and not an intermediate like this. So we got to go substitute it, and we can use the first rate law, which is 2 bromines or diatomic bromine is equal to, and then we have the coefficient 2 there, means that this bromine is going to be have a square relationship here, and then we can just algebra square root both sides, bromine. I just turn them on borons, 1 second. And then if you plug, if you have your one bromine is equal to your half equivalent of diatomic bromine, you can plug that into the first again and write it. That, and you can keep that it since it's, yeah, it's probably, and so that's the same as what they had up there, so it is consistent.
So excellent. So that looks good. So did everybody follow that? I copied that. And that was excellent. Any questions on that first part? So we should feel comfortable, right, doing this on our own, substituting. All right, good. So what are the units of our rate constant then? So this is kind of interesting. So take a minute, try to figure this out if you haven't already. So you have this. Yeah. Yeah. Since it's two of them, so then, yeah. So what do we get for our units for this one, for our K? So this is a little weird. So we have our bromine to our half order, right, hydrogen, and so we want to figure out our rate. We want to figure out change of bromine, oops, over our time. And so we said that's equal to, I'm just rewriting our rate constant. And so then what do our units of K have to be to cancel out? So we need to get rate and molarity per second. And then we have a bunch of weird things going on here. So we have molarity, right, molarity 1/2. And so that means our K, to get rid of, we have to get rid of molarity 1/2. So we have to do liters 1/2 molarity, negative 1/2, and then per second for our K. And then let's look at this last one. So is it possible that this reaction occurs in a single mechanism? And so if it were to occur in a single mechanism, what would the rate law be? So take a few minutes to ask your neighbor about that one. So what are some thoughts on this? Do you think it could occur in a single step mechanism? So I see some no's. You say what? That it could occur in a single step? So what would the reaction rate be though if it occurred in a single step mechanism though? Well, right, we could look at this. So right, if this was just a single step, so just looking at our overall reaction, right, what would the rate have to be dependent on then? So did everybody catch what he said, right? So it would have to be based upon the H2 and bromine concentrations, right, initially. So our rate law would have had to have had, you know, first order of both diatomic bromine and hydrogen, just like Alira said. But since it was this weird half mechanism, then that's kind of telling us, right, not a single step mechanism. So that's where, right, our kind of expected single step mechanism does not match our observed. And, you know, that's how you start getting into, well, what is the mechanism? Because then obviously it's not single step. So that gives us a hint to this. All right, let's try some more math. So this one will be a good practice. Sorry, these book problems are kind of long, so hopefully they all fit. Can people read that? It's 61 in the book, and I have the book if anybody can't read that. And so it says hydrogen peroxide decomposes, and so you may know this, right? It decomposes spontaneously. That's why hydrogen peroxide are always in those dark bottles so that you don't have any light that would contribute to this decomposition. And so you can see it breaks down to water and oxygen. You've also seen this decomposition catalyzed. And it says the activation for this reaction is 75 kilojoules per mole, so watch that unit. And in the presence of a metal catalyst, the activation energy is lowered to 49 kilojoules. And so let's just start with A. What temperature would the non-catalyzed reaction need to be run at to have a rate equal to that of the metal catalyzed reaction? So I'll give you guys a few moments to at least stare at it, and then maybe I'll give you a hint. So let's at least kind of check in. Where are people? What formulas are we thinking about using? This could be a tricky one to. Sorry, what did you say? A times what? E to the. Perfect. So this looks like a good start. So did everyone at least kind of start with that? No? So where do we go from here? So what could we do / what is it asking us to do?
It gives us activation, which is a great time for temperature. We could set them equal to each other, the rate equal to each other, because it wants it to be when the rate is equal, what temperature we should do that, and something like that.
Yeah, excellent. Is that what you did too, Tori? Do one of you want to put it on the board or tag team that or something? Lay it out.
I don't know what A was, so I never really got, I'd be.
Well, A.
No, but A is available.
Yeah, so A should eliminate. Tori, do you want to put it on the board or at least start it? You can put it on that far board. And you don't have to be perfect. It just sounds like you started off at least correctly. So let's just see where everybody's at in the class too. Because I'm not sure if everybody started with that. Equal to. Yeah. Okay.
Oh, you have probably end up taking the natural log to get that down. So it's just after that.
So do we at least get to here? So right, Tori did this setup correctly, right? So we have our first activation energy, and we're trying to solve at what T, right? It's going to be equal to. We said our second condition was our metal catalyzed reaction. And then again, Tori plugged in the correct conditions. So we said, what temperature do we need it to be? So there's our 8.314 times our 298. And so then at this point, it's just algebra. So let's set them equal to each other. And so let's see, so then we can take the log of both sides. So we get natural log of A minus this stuff over RT is equal to ln minus and so then we just need to solve. And so A should cancel. So let's start plugging stuff in. And -1. And so now we're at 7500 RT. And you can check my math. Make sure I didn't screw up. Oh, I don't think I got the right answer. Oh, I left off a 0. Sorry. Let me try that one more time. So divided by, do you see my mistake? I left off 1 0 there. 75000. Okay, one more time. Now inverse that. So that looks right. So 457 Kelvin. So did everybody get that once we did the algebra? And then of course we can convert it back to Celsius. So about 183 Celsius roughly. Oh my gosh. All over the place today. Questions about that one? Oops. And so let's try B then. So continuing on. So the enzyme catalyst found in blood lowers the activation energy even further. And so now figure out at what temperature would your non-catalyzed reaction have to run at. So see if you can repeat that process now that we've seen it.
I presume it means that the enzyme catalyzed reaction is at 25 degrees Celsius.
Yes. Yeah. So let's still assume 25 degrees Celsius. It doesn't say anything different. All right, how did this problem go? So I assume we set up something pretty similar, so I'll just start at least outlining what we should have done. So again, pretty similar to our setup previously, except new activation energy of 8,000. And so now just solving again. Oops. Negative 8,000. And so what do people get for their temperature as I plug this in? Any brave guesses? Yeah, you said 2,500 degrees Celsius? Yep, that's at least what my answer key is showing, so I'm still plugging it in. Did other people get that? Yeah, I should confirm that once I finish plugging, if I can keep my variables straight. Oh, I think I screwed something up. Times. So I get that, so my answer is in Kelvin, so about 2,800 Kelvin, which matches the 2,500 Celsius. Questions on that one? Should just be some algebra. So let's look at another one from the book. And this one has a little star on it, so it is tricky. But I wanted to go over it because it has to do with the steady state approximation, which, if you recall, we did yesterday, or not yesterday, Tuesday for our derivation of our enzyme. And so I wanted to see if we could try that again and how to do that steady state approximation. And again, we'll kind of go through it together. So we have this reaction, so good old N2O5 now, so two of them. They go to make 4 equivalents of NO2 plus oxygen. And so here's a proposed mechanism with 3 steps there. And so your first step is N2O5 breaks down to NO2 and NO3. And again, this is 1872 if you need a better look in your book. And so then it's saying assume a steady state condition. And again, see if you can figure that out. Otherwise, we can go over what that is telling us to do. And then see if you can prove this shown rate law here. So where are we in this problem? What are we thinking? Where do we start? Where could we start? And it kind of gave us a hint, right? So let's kind of focus on our oxygen. And so if you didn't know where to start, a good place to start would be, well, how do we quantify how much oxygen is being produced? And so what of these equations, which one involves oxygen production? So only two. So right, so now we can look at 2 here. And so we're saying, okay, well that means based off of 2, that's some sort of rate of oxygen over time has to be dependent on, right, our K2 times, and then, right, just based off of these concentrations, so NO2 and NO3. So this was a good first step, right, just writing that out. And so what's the problem with this? Yeah, so I'll just repeat. So basically, it's not in terms of our reactants, right? So we only have N2O5 as our reactant, so that's what we have to put it in terms of. And so we could also, kind of star this. Well, this is our intermediate, so we can't just leave that. And so it says steady state, but before we start getting into what that means, let's just quantify, well, where is NO3 formed? And where is it consumed? And so let's just break that down explicitly. So we can say our rate of formation then of NO3. So where is NO3 formed? Or what's the expression that dictates that? So the first one, excellent, right? So it makes NO3. And so that is going to be equal to our K1 times N2O5. Okay. And so let's see. I think that's the only way it's formed. So now let's see where it is consumed. So now NO3 consumed. And so just like we did with that enzyme substrate derivation, we said, okay, well, it can also be consumed in the reverse reaction. So that's one way. So our reverse reaction, so K -1 times, so then it has to be times NO2, our products times NO3. And then how else is our NO3 consumed? So what other equation? Yeah, so K2, right? So just writing this expression then. So the NO2 times NO3 times our K2 is our rate of consumption. And we should add them, right? Showing that these are both ways that they're consumed. And so then for steady state approximation, all that is meaning is that the formation equals consumption. So now I'm just going to write these two expressions equal to each other. So now we're saying, okay, well that means that as soon as we make some NO3, then it's going to be consumed by those processes. So now I'm just rewriting this. And so is everybody here? So once you get to here, then we just can solve for NO3 at this point and put it in terms of everything else. And I think from there, everything should line into place, but let's do that. So solve for NO3. So now just a bit of algebra. So I'm just going to rewrite this for a second and then pull out my NO3 from this expression. Oops, sorry. So all that times our NO3. And so now dividing, so we should get concentration of NO3 is equal to K1 N2O5 divided by this expression, so K negative 1 times NO2 plus K2 NO2 and so then we could further just simplify this even, so K1, I'm just rewriting this, basically pulling out, so K1, negative 1 plus K2 times our concentration of NO2. So I just rewrote that there. And so now that we have solved for our NO3, we should be able to plug it back into this expression. So times our NO2. And let me rewrite that for a second. So plug into what we had said. So we said K2 times NO2 times NO3. So now plugging in this expression. And so then this cancels out, our NO2 cancels, leaving us with what they had said. So now we get K1 times K2 times N2O5 divided by K2 plus K1, negative 1. And is that what they were asking for? So yes, we did indeed get that same expression. So I'll kind of leave that there for people to finish digesting. Any questions on anything that we've covered or homework or any other last minute things? All right, so let's go ahead. That's a good place to stop. So let's get ready to take our quiz. So I'll hand out our quiz. And of course, if you want to take a break, take a break. And then I'll try to bug some of you individually. They were asking me questions. So some of you have been throwing Excel plots at me. So that's great. So then I can help you with your Excel plots for the last lab. And then any other issues on the homework, just let me know and we can go through them. All right, I'll hand out the quiz. So just take your time with it, read everything. And again, you can take a break if you need. Yeah, that's fine. Yeah, you can just give it back to me if you do. No, individual quiz today. I think you'll be okay. I still need to put in your buddy quiz grades. I've been slacking.